Hello everyone, my name is Chantel, and in this all-deck Active-HDL video, I'm going to demonstrate the Design Profiler. What this tool does is that it shows how the CPU is utilized when simulating a design. It does this by counting the number of CPU ticks that each HDL statement, design unit, or instance of a design unit uses during simulation. This tool helps identify areas in a design where it puts the greatest amount of strain on the simulator. And this information can then be used to optimize the performance of your simulation environment, potentially making the simulation process more efficient. So now to demonstrate this tool, I have this example design called Data Path opened, and you can find this yourself by going to Help, Open Example, Samples, VHDL Designs, and then Data Path. Now, there are two ways to go about getting profiler data. The first way is to go to the Designs Settings, go to the Coverage Profiler category, and click on Profiler. And notice that you can only choose either ACDB coverage or profiler. You cannot collect data for both. Also, there's a profiler subcategory where you can choose your output directory and enable the collection data for all units. This means that you'll be collecting profiler data for objects from your current working library and also from the other resource libraries being used during simulation. When you're done with the design settings, click Apply and then OK to save the settings. And from there, just make sure your files are compiled, and then initialize and run your simulation. The second way, which I'll be demonstrating in this video, is by using macro commands. In the runme.do macro, in the asym command line, I've removed the advanced data flow argument, and now I'm going to pass the argument profiler instead. If you want to collect data for all units, like in the option in the design settings, just type profiler_all. Another important command I want to demonstrate is the command that generates a profiler report. A report can be saved as a text, CSV, or HTML file. I want to generate an HTML report, so to get this report, at the next line after the last line of the macro file, I'm going to use the command profiler report followed by -html and then the name of the file, which I'll name it sim1.html. So now, with the commands in place, I'm going to execute this macro to get the simulation results. After the simulation has finished running, the console shows a profiler comment confirming that the profiler results have been saved. By default, the results get saved in the profiler folder of the design as a .tbp file. If the folder didn't exist prior to the simulation run, a new profiler folder will be created. I'm going to first open up the HTML report I generated. So I'm going to open a file and go to the design's source folder. And in here, there's my sim1.html profiler report, which I'll click on and then open. Now I have the HTML report opened up in Active-HDL. The first tab we see is the Summary tab. This contains information about the number of accepted ticks and timings, the number of all ticks and timings, and the acceptance ratio. This ratio shows how many timings were accepted as reliable, and how much of the accepted timings account for the total simulation time. In this case, we can see that this percentage of timings were reliable, and these accepted timings only took up this percentage of total simulation time, which is quite low. Already, this is telling me that a lot of my simulation time is being used somewhere else. And this can happen if your simulation machine is performing other tasks, but a little more on that later. There are other tabs on this report. There's this Units tab, where there's a list of the design units along with their total percentage CPU usage during simulation. Clicking on any unit displays a comprehensive list of that CPU unit's timing, showing what line of code was executed, how many CPU ticks that line used, how many timings it had, and the average of the total ticks over the number of timings. The Hierarchy tab shows similar information, but shows information of each individual instance of a unit in a hierarchical format. And notice that there's a line called Other Code that took up a majority of CPU time. So this is the profiler report in HTML format. Now I'm going to go ahead and close it, and I'm going to now use the profiler viewer. This is a standalone application that displays the performance data that was collected. To access this, head over to Tools, and then click on Profiler Viewer. Now in this window, click on the Open File button, go into the Designs Profiler folder, and we're going to use the profiler.tbp result file that was saved earlier. And now we have our profiler results loaded up, and I can talk about this viewer window. Here we have our main menu with sub-menus for File, Edit, View, and Help options. This toolbar has buttons for opening the profiler file and reloading the profiler data, a display for the CPU frequency, and buttons for display settings, filter options, and buttons for organizing, bookmarking, and navigating through HDL code when we look at the profiler data. So currently, in the main space of the window, I'm in the Hierarchy tab. When I click on an item in any of the tabs, a new section pops up on the right side, showing a Details section, as well as the item's source code with some details that I'll talk about in a bit. On the left-hand side, we have the elaborated structure of the design and the profiling statistics for each item in the design tree. As you expand the design, you can see that data is shown for each individual instance of a unit. The data collected are shown in these columns. There's the number of CPU ticks that were required for execution during simulation, the share percentage in the total simulation time, the time in microseconds, which is calculated from the number of CPU ticks and CPU frequency, and then the next three columns are the same type of statistics, but this time it includes the highlighted object as well as all other objects further down in the hierarchy. In the Details tab are pie charts. These pie charts visually demonstrate how much CPU time the selected item used during the simulation run, with the selected item in red and the rest of the design in blue. The second pie chart shows the results along with the selected item's children. The tabs outside of the Hierarchy tab will only display one pie chart since hierarchy isn't taken into account. And now I'll talk about the Source Code tab. This tab shows CPU tick counts for each HDL statement of the selected item that was profiled during simulation. There are columns that show the line numbers of the source file, the total number of CPU ticks for each line of HDL code, and the source code display. This little margin in between the ticks and source column can display bookmarks and the expand or collapse widgets. Notice that some source code lines are differently colored. The red lines indicate that it had a non-zero share in simulation time. The gray lines are non-executable lines, or lines that do not belong in the selected design unit or instance of that design unit. And the lines in blue are executable code that was not hit during the simulation process. So this is what the main display area of the profiler viewer shows. Even though there are different tabs, the information layout is similar throughout. Clicking on this Processes tab displays data for all the individual processes in the design hierarchy. This means each instance of a design unit is shown as its own item. Clicking on the Units tab shows profiling data for all units in the design. If there are multiple instances of a design unit, the profiling data of all instances are combined. This Processes tab displays the merged data of each process profiled. This is basically combining all the multiple instantiations of each process seen in the Other Processes tab. And this last tab just lists all the subprograms that weren't executed during the simulation process. This tab can show two groups: external subprograms and local subprograms. As you may have already noticed as early as the HTML report, the other code takes precedence over the actual test bench code because it's taking up a lot of CPU time. This is happening because, if you recall, the macro had commands for the accelerated waveform viewer. During the time that simulation was initialized, waveforms were also being generated for signals. So I'm going to remove some commands to optimize my simulation. I'll go ahead and remove all the wave commands, and I'll change the name of this HTML report to HTML2, since this is the second simulation run. And now I'll just execute this macro section. Now I'll open Sim1 as well as Sim2. Now notice that more of the reliable timings took up more CPU time compared to the first simulation run. And the total number of CPU ticks taken up is significantly smaller compared to the first simulation run. In the Profiler viewer, all I have to do is reload the Profiler data to update it to the new simulation run results. And as you can see, the test bench code is now taking precedence in the hierarchy over the other code, since there's nothing else happening during simulation besides the simulation itself. You can also see here how much faster the simulation ran this time around, increasing the speed at which you can simulate this design. And that wraps it up for this video on the Design Profiler. This tool provides useful data for optimizing your design in many different scenarios, like a design that needs to optimize file access routines, or maybe a design that needs partitioning of its modules between the software simulator and a hardware accelerator. Whatever the case may be, the Profiler is there to help you find ways to improve your simulation runs. If you'd like to see more details on this tool, go to Help, either PDF or HTML documentation, then Product Help, and search for Design Profiler. Thank you for watching.